Good morning, world. Today I'm going to discuss about a very familiar topic in inorganic chemistry, that is the crystal field theory. And what is this crystal field theory? Absolutely, first year know what is crystal field theory, because this crystal field theory is very important in coordination chemistry. Okay, when you discuss about what the meaning of the crystal field theory, it is a it is a electrostatic model, and we are simply use it we are simply uses the ligand electrons to create a electric field around the metal center. I think you can get this point right, because we know in when we are approaching for the inorganic chemistry or the coordination chemistry, we know that we are dealing with metal centers and ligands. Okay, we are dealing with metal centers and ligands, because we know that when we are discussing about coordination chemistry, there are many structures that coordination complexes can take off. They are especially taking off many different structures. And as we know that the main common or the majority of the complexes are being octahedral, tetrahedral, or square planar. They can take any of these geometries. Other than that, there are many geometries, but in the common exam points, or when you are discussing about the coordination chemistry, the main geometries that we are coming to our mind is octahedral, tetrahedral, and square plane. If we take octahedral complexes, today I'm going to discuss mainly about the octahedral complexes. If we take about octahedral complexes, we know that normally the d orbitals have five orbitals in the d orbit, like as dxy, dxz, dyz, dz squared, and dx squared minus y squared. Because these all orbitals are degenerate, that means they have same energy. They all have same energy. But we know in octahedral complexes mainly the ligand approaches the metal center via the axis. That means along the axis the ligands are approaching. We know that when ligands approach there will be attraction towards the metal, and also repulsion from electrons in the d orbital. Electrons in the d orbital. As we can see in here, these orbitals, this dz squared orbital and dx squared minus y orbital are in the axis. Therefore, the repulsion between dz squared and dx minus squared orbitals with ligands will get more than the dxy, dxz, and dyz orbitals. Due to that, what happened? The degenerate d orbital get separated into two portions, like this, because we know we have same energy, five orbitals, same energy, five orbitals, what happened now, because I discussed about that, due to these repulsion forces, this dz squared and dx squared minus y squared orbitals get split into high energy, and these orbitals split into low energy because these are in degeneration before ligands are approaching. When ligands approach, because when in octahedral complex ligand approaching the true axis, these the interaction between the orbitals in the axis and the ligand will be get, I mean like the repulsion between these orbitals and the ligand will get increases, and they are splitting into high energy while other orbitals get splitting into low energy. Because this getting splitting, this energy is called as crystal field stabilization energy, or we call CFSE, crystal field stabilization energy. From here we are using a symbol called delta oct. Especially we can see that by this amount of energy, these two orbitals get increase. That means if we consider, if we have like one these orbitals get increased by, because there is three orbitals, this dz squared and d squared d squared minus y squared orbitals energy got increased by plus 0.6 compared to dxy dyz dx orbitals, and these orbitals get lower energy with compared to these two orbitals by minus 0.4 energy. Therefore, we can say that the crystal field stabilization energy will be the gap between this. This energy gap might be this energy gap might vary, this delta vary according to the ligand oxidation state, mainly depend on the ligand and the oxidation state, because we know that ligands two types as weak field ligands and strong field ligands. Due to having high oxidation state, this splitting energy also getting increased. Because I will discuss about weak field ligand and strong field ligand in another video. If you are I will discuss on them in another video, because I don't have any time to discuss the same thing in this video, because I think you know about the